There is a moment in every civilization's history when a single discovery shatters the known world and replaces it with something far larger, far stranger, and far more beautiful than anything previously imagined. When Galileo pointed his crude telescope toward the night sky in 1610 and watched the moons of Jupiter trace their silent orbits, he did not merely discover new celestial bodies, he demolished the idea that everything in the cosmos revolved around the Earth. When Edwin Hubble confirmed in 1924 that the faint, fuzzy smudges astronomers called nebulae were in fact entire galaxies, island universes containing hundreds of billions of stars, the observable universe expanded overnight from a single galaxy to something almost incomprehensibly vast. We are living through one of those moments right now. On July 12, 2022, NASA released the first full-color scientific images from the James Webb Space Telescope, and the world held its breath. What appeared on screens around the globe was not just a beautiful photograph, it was a window into time itself. A single image called Webb's First Deep Field showed thousands of galaxies compressed into a patch of sky smaller than a grain of sand held at arm's length, and among those galaxies were structures so ancient that their light had been travelling toward us for over 13 billion years. Light that began its journey when the universe was less than 1 billion years old, when the first stars were just beginning to ignite in the primordial darkness. But the truly astonishing part was not the beauty of the image. It was what the image contained that science had not fully predicted. What the James Webb Space Telescope found, in image after image, observation after observation, was a universe that refused to behave according to our best models. It was a universe that seemed to have been making large, complex, mature galaxies far too early in cosmic history. A universe that appeared to be more structured, more organized, and more active in its earliest moments than our theoretical frameworks had suggested was possible. The James Webb Space Telescope, in short, looked too deep into space and found something that demands we rethink everything. This article is not simply a summary of Webb's discoveries. It is an exploration of what those discoveries mean, scientifically, philosophically, and existentially. We will journey through the telescope's engineering marvel, its unprecedented capabilities, and the specific findings that have startled cosmologists worldwide. We will examine the scientific debates those findings have ignited, the theoretical models being revised or discarded, and the new questions emerging from the wreckage of old certainties. But beyond the science, we will also ask the deeper questions that great discoveries always provoke. What does it mean for our understanding of cosmic history that the earliest universe appears to have been far more organized and structured than we thought? What does it mean for our models of dark matter and dark energy when the galaxies we observe refuse to obey our predictions? What does it mean, philosophically, for human beings to peer 13 billion years into the past and realize that the story of the cosmos is stranger, richer, and more mysterious than we ever imagined? The James Webb Space Telescope is more than an instrument. It is a philosophical provocation. It is a reminder that reality is always more vast than our current map of it, and it is an invitation, urgent, thrilling, and humbling, to begin drawing a new map. Throughout this article, we will grapple with several core questions. Why were large, mature galaxies present in the very early universe, when our standard cosmological model suggests they should not have had time to form? What does this tell us about the processes of galaxy formation, star formation, and the role of dark matter in the early cosmos? How is the James Webb Space Telescope rewriting our understanding of the first light, the period when the universe transitioned from a dark, formless soup of hydrogen and helium into a cosmos blazing with the first stars and galaxies? What are the implications for the lambda CDM model, the standard model of cosmology, when observations consistently reveal structures that seem to challenge its predictions? And beyond the purely scientific questions, what does it mean, philosophically and existentially, for human beings to be the kind of creatures who can build a machine, launch it into space, point it at the ancient darkness, and read the story of time written in light? These are the questions that animate this exploration. Let us begin. Human beings have been looking at the night sky since before recorded history. The stars provided navigation, marked the seasons, and filled the imagination with stories of gods, heroes, and monsters traced in the patterns of light. But for most of human history, the stars were simply points of light, beautiful, mysterious, and utterly unreachable in their meaning. The invention of the telescope in the early 17th century changed everything. Suddenly, the blurry disk of Jupiter resolved into a world with moons. The pale smear of the Milky Way dissolved into countless individual stars. The moon revealed craters, mountains, and plains. For the first time, human beings could extend their senses beyond the biological limits of the eye and reach toward the cosmos. Over the centuries that followed, telescopes grew larger, more powerful, and more sophisticated. Each generation of instruments brought new revelations. The spectroscope allowed astronomers to analyze the chemical composition of starlight. Photography captured images too faint for the human eye to detect. Radio telescopes opened an entirely new window onto the universe, revealing cosmic phenomena, pulsars, quasars, the cosmic microwave background, invisible to optical instruments. And then in 1990, humanity launched the Hubble Space Telescope, a device that would prove to be perhaps the most scientifically productive instrument ever built. By escaping the blurring effects of Earth's atmosphere, Hubble could achieve a clarity of vision impossible from the ground. Its famous deep field images, long-exposure photographs of tiny, seemingly empty patches of sky, revealed thousands of galaxies stretching back billions of years in cosmic time. Hubble confirmed the expansion of the universe and helped pin down its age at approximately 13.8 billion years. It observed the birth and death of stars, probed the atmospheres of distant worlds, and delivered image after image of cosmic splendor. But Hubble had limits. It was primarily an optical and ultraviolet telescope, and it could see only so far back in time. The most ancient galaxies, those formed in the first few 100 million years after the Big Bang, had their light stretched by the expansion of the universe into the infrared range of the spectrum, beyond Hubble's primary capabilities. To see those first galaxies, astronomers would need a fundamentally different kind of instrument. The James Webb Space Telescope is, in almost every sense, an extraordinary engineering achievement. Its development took over 2 decades, involved contributions from more than 300 universities, organizations and companies across 29 countries, and cost approximately $10 billion. At multiple points during its development, it faced cancellation, budget overruns, technical challenges, and delays. The fact that it exists at all is a testament to the determination, creativity, and patience of thousands of scientists, engineers, and technicians. Webb's primary mirror is 6.5 meters in diameter, more than 2.5 times the diameter of Hubble's primary mirror. Because the mirror was too large to fit inside any existing rocket fairing in its deployed configuration, it had to be designed to fold up like an origami construction for launch, and then unfold perfectly in space. The mirror consists of 18 hexagonal segments made of beryllium, a lightweight strong metal, coated with a thin layer of gold to enhance their reflectivity in the infrared. The telescope operates not in visible light but primarily in the infrared, wavelengths of light that correspond to heat radiation. This is crucial for 2 reasons. First, as mentioned, the most ancient galaxies have had their light redshifted into the infrared by the expansion of the universe. Second, infrared light can penetrate dust clouds that block visible light, allowing Webb to peer into star-forming regions that Hubble could not see through. But infrared astronomy presents a major challenge. Anything warm emits infrared radiation, including the telescope itself. To prevent the telescope's own heat from overwhelming the faint signals it is trying to detect, Webb must be kept extraordinarily cold, around -233 degrees Celsius, just 40 degrees above absolute zero. To achieve this, the telescope is equipped with a sunshield the size of a tennis court, a 5-layer membrane made of a Kapton-like material called Kapton E, aluminized and coated to reflect sunlight away from the telescope's instruments. Webb orbits at the second Lagrange point, or L2, a gravitationally stable point about 1.5 million kilometers from Earth in the direction away from the Sun, where its sunshield can always block the light and heat of both the Sun and the Earth. The deployment sequence after launch was one of the most nerve-wracking events in the history of space science. Webb had to execute 344 single point-of-failure steps, any one of which, if it failed, could have doomed the mission entirely. The sunshield had to unfurl, the secondary mirror had to deploy, all 18 primary mirror segments had to unfold and lock into position. The entire process took 2 weeks, during which engineers and astronomers around the world held their collective breath, against all odds, and against the historical tendency of complex systems to fail in unexpected ways, every step executed perfectly. When the first test images were released in early 2022, even the engineers who had built Webb were astonished. The images were not just good, they were extraordinary. Star fields that Hubble would have captured as blurry smudges resolved into perfect, sharp points of light. Galaxies at the edge of the observable universe emerged from the ancient darkness with a clarity no human instrument had ever achieved. To understand why Webb's discoveries are so significant, it is essential to understand one of the most profound facts about light and distance in the cosmos. When we look at distant objects, we are looking back in time. Light travels at approximately 209,792 kilometers per second, the fastest speed possible in our universe. When we observe a galaxy 13 billion light-years away, We are seeing light that left that galaxy 13 billion years ago. We are not seeing the galaxy as it is now. We are seeing the galaxy as it was 13 billion years ago, when the universe was less than a billion years old, when the first structures were just beginning to emerge from the primordial darkness. In this sense, powerful telescopes are not just instruments for studying space. They are machines for studying time. The deeper into space we look, the further back in time we see. The James Webb Space Telescope, with its extraordinary sensitivity in the infrared, can see further back in cosmic time than any instrument before it. It can observe galaxies that formed within the first few 100 million years of the universe's existence. The cosmic equivalent of looking at a photograph of someone taken the day they were born. The universe's expansion plays a crucial role in this cosmic time machine. As space expands, the wavelength of light travelling through it stretches, a phenomenon called cosmological redshift. Light that left the earliest galaxies as ultraviolet or visible light has been stretched by the expansion of the universe over billions of years into the infrared range by the time it reaches us. Webb's infrared instruments are perfectly suited to detect this ancient, redshifted light. Webb carries four main scientific instruments: the near-infrared camera, NIRCam, the mid-infrared spectrograph, and the near-infrared imager and slitless spectrograph. Together, these instruments allow Webb to capture images of unprecedented depth and clarity, analyze the chemical composition and physical properties of distant galaxies through spectroscopy, study the atmospheres of exoplanets, and observe the formation of stars and planetary systems within our own galaxy. The combination of Webb's large mirror, its infrared capabilities, its cryogenic temperature, its L2 orbit, and its suite of sophisticated instruments makes it, by almost any measure, the most powerful astronomical observatory ever built. And what it has shown us has forced astronomers to confront a universe more complex and surprising than their best models predicted. When NASA released Webb's first deep field image on July 11, 2022, the image appeared to show a crowded, rich tapestry of light. Thousands of galaxies of different shapes, sizes, and colors populated the frame. Gravitational lensing, the bending of light by massive foreground galaxy clusters, stretched some background galaxies into arcs and rings, creating a visual demonstration of Einstein's general relativity playing out across cosmic scales. But as stunning as the image was visually, the scientific data it contained was what truly astonished astronomers. Careful analysis of the image began revealing something unexpected. Many of the most distant galaxies, those from the earliest epochs of cosmic history, were larger, brighter, and more structurally evolved than the standard model of cosmology had predicted they should be. The standard cosmological model, known as lambda CDM, for lambda cold dark matter, makes specific predictions about how galaxies should form and grow over cosmic time. According to this model, the early universe should have been dominated by small, irregular, chaotic proto-galaxies that only gradually merged and grew into the large, well-organized structures we see today. Large, massive, well-formed galaxies should be rare in the early universe, because there simply hadn't been enough time for gravity to assemble them. What Webb found instead were galaxies in the early universe, some observed at redshifts corresponding to the universe being less than 700 million years old, that were far more massive, far more organized, and far more luminous than the models predicted. Some of these galaxies appeared to contain as many stars as the Milky Way does today. Despite having formed in what should have been the cosmic equivalent of an infant universe, this was not a minor discrepancy. This was a challenge to one of the foundational assumptions of modern cosmology, the too many, too big, too soon problem. The scientific community has given this finding an informal but apt description: the too many, too big, too soon problem. Webb is finding massive galaxies in the early universe in numbers and sizes that the standard model does not predict. Several specific discoveries have crystallized this problem. In late 2022 and early 2023, a team of astronomers led by Ivo Labbe of Swinburne University published a paper in the journal Nature describing the discovery of 6 massive galaxy candidates at redshifts between 7 and 10, corresponding to an era when the universe was between 500 million and 800 million years old. These galaxies appeared to have stellar masses comparable to the Milky Way, masses that, according to the standard model, should require billions of years of star formation to accumulate, not hundreds of millions of years. The paper, titled A Population of Red Candidate Massive Galaxies 600 Mile After the Big Bang, sent shockwaves through the cosmological community. The authors themselves were cautious, noting that these were photometric redshift estimates subject to revision, and that some of the objects might prove to be closer, lower-mass galaxies misidentified through the limited color information available in the initial imaging data. But when spectroscopic follow-up confirmed some of the redshifts, the challenge to the standard model became harder to dismiss. Astronomer Alison Kirkpatrick of the University of Kansas, one of the authors of the paper, put it bluntly in a public statement: "We've found something that's super unexpected. These galaxies should not exist." This kind of candid admission from a professional astronomer carries enormous weight. In a field where understatement is the norm, "should not exist" is a phrase that signals a genuine crisis of understanding. Further observations have continued to accumulate evidence of this discrepancy. Webb has identified multiple galaxy candidates at extreme redshifts, some potentially at Z greater than 12 or even 16, corresponding to epochs when the universe was only a few 100 million years old. While the most extreme candidates remain subject to spectroscopic confirmation, the overall trend is clear. The early universe contains more massive, more organized galaxies than the standard model predicted. Among the extraordinary objects Webb has revealed, one stands out as particularly significant. In 2024, astronomers using Webb's JWST Advanced Deep Wave Extragalactic Survey program confirmed the spectroscopic redshift of a galaxy designated JWST GS14-0. This galaxy has a confirmed redshift of approximately 1432, placing it at a look-back time of about 13.5 billion years, meaning we are seeing this galaxy as it existed just 290 million years after the Big Bang. What makes JWST G14-0 remarkable is not just its distance but its properties. The galaxy is relatively bright, meaning it is actively forming stars at a significant rate. Spectroscopic analysis reveals signatures of oxygen, a heavy element that can only be produced inside stars through nuclear fusion. The presence of oxygen in a galaxy this early in cosmic history implies that multiple generations of stars had already been born and died in this galaxy within the first 300 million years of the universe, an astonishing rate of stellar evolution. The existence of oxygen this early presents a profound challenge. In the standard model, the first stars, known as population 3 stars, formed from pure hydrogen and helium, the only elements produced in the Big Bang. These first stars had to live and die, exploding as supernovae and seeding the surrounding gas with heavier elements before subsequent generations of stars could form containing those heavier elements. The chemical enrichment of galaxies was expected to be a gradual process. Finding oxygen, a product of stellar nucleosynthesis, in a galaxy just 290 million years old implies that this entire cycle of stellar birth, life, death and chemical enrichment happened extraordinarily quickly. This finding has profound implications for our understanding of population 3 stars, the initial mass function of the first stars, the efficiency of star formation in the early universe, and the feedback mechanisms that regulate how quickly galaxies grow. It suggests either that our models of early star formation are significantly wrong, or that the standard cosmological model needs substantial revision in how it treats the earliest epochs of cosmic history. Webb's observations have also dramatically illuminated our understanding of the large-scale structure of the early universe, what cosmologists call the cosmic web. The universe is not uniformly filled with matter. Instead, matter is organized into a vast, three-dimensional network of filaments, sheets and voids, like a gigantic cosmic spider's web, or perhaps more accurately like a sponge on the largest possible scales. At the nodes where filaments intersect, galaxy clusters form, the densest, most massive structures in the universe. Between the filaments lie vast cosmic voids, regions almost completely empty of matter that can stretch for hundreds of millions of light years. Webb's deep field observations have revealed hints of this large-scale structure even in the very early universe. Galaxies in the early cosmos do not appear to be randomly distributed. They appear to be organizing themselves into protoclusters, the seeds of what will become the massive galaxy clusters we observe in the later universe. This early organization of matter into the filaments and nodes of the cosmic web suggests that the gravitational scaffolding provided by dark matter was already shaping the distribution of visible matter very early in cosmic history. One particularly striking observation was the discovery of what appeared to be a protocluster of galaxies at a redshift of approximately 7.7, corresponding to an age of less than 700 million years. This protocluster contained several galaxies grouped together in a region of space that would eventually become one of the most massive structures in the universe. Its existence so early in cosmic time pushed back our observational evidence for the formation of large-scale structure, and hinted that the cosmic web was assembling itself faster than standard models had suggested. One of Webb's primary scientific goals is to probe the epoch of reionization, one of the most dramatic phase transitions in the history of the universe. After the Big Bang, the universe was initially filled with a dense, hot plasma of particles so energetic that no neutral atoms could form. As the universe expanded and cooled over approximately 380,000 years, this plasma cooled enough for electrons to combine with protons and form neutral hydrogen atoms, an event known as recombination. The universe became transparent for the first time, and the radiation released during recombination became the cosmic microwave background that we can still detect today. After recombination, the universe entered what astronomers call the Dark Ages, a period lasting hundreds of millions of years during which there were no stars, no galaxies, and no sources of light. The universe was filled with a diffuse fog of neutral hydrogen and helium, slowly contracting under gravity into the first structures. Then, somewhere between about 150 million and 800 million years after the Big Bang, the first stars and galaxies ignited. The ultraviolet radiation they produced was energetic enough to strip electrons from the surrounding neutral hydrogen, a process called ionization. Gradually, bubble by bubble, the cosmic fog of neutral hydrogen was cleared away, and the universe became transparent again, this time to ultraviolet and visible light. This process, called reionization, transformed the universe from a dark, foggy place into the clear, star-filled cosmos we inhabit today. Webb is revolutionizing our understanding of this epoch. Its observations are showing that reionization was not a uniform process. Different regions of the universe were ionized at different times, depending on the proximity of early ionizing sources, massive, hot stars and active galactic nuclei. Webb is also helping astronomers understand which sources drove reionization, whether it was primarily the ultraviolet radiation from young massive stars in early galaxies, or whether active galactic nuclei, AGN, the luminous cores of galaxies powered by actively accreting supermassive black holes, played a more significant role than previously thought. This question matters enormously for our understanding of the early universe. The sources and timing of reionization directly influence the thermal history of the intergalactic medium, the formation of the first galaxies, and the subsequent evolution of cosmic structure. Webb's spectroscopic observations are providing new, detailed information about the state of the intergalactic medium at different epochs, allowing astronomers to map the progress of reionization with unprecedented precision. Among the most startling findings from Webb has been the discovery of supermassive black holes containing millions or even billions of times the mass of the Sun, at extremely high redshifts. These black holes power what are known as quasars, extraordinarily luminous objects that shine more brightly than entire galaxies, powered by the energy released as matter falls into the black hole. Supermassive black holes have been a cosmological puzzle for decades. Even before Webb, ground-based and space-based telescopes had detected quasars at redshifts above 6, corresponding to ages less than 1 billion years. But how a black hole can grow to contain 1 billion or more solar masses within the first 1 billion years of cosmic history is deeply problematic for standard theories of black hole growth. In the conventional picture, black holes grow by accreting matter. There is a theoretical limit, known as the Eddington limit, to how fast a black hole can accrete matter, because the radiation pressure from the accreting material tends to blow away the infalling gas. If a black hole grows at the Eddington limit continuously from a stellar mass seed of perhaps 100 solar masses, it would take billions of years to reach the masses inferred for the earliest quasars. Even with super Eddington accretion, or with seeds from the direct collapse of massive gas clouds rather than from stellar mass black holes, explaining the most massive early black holes is challenging. Webb has deepened this puzzle considerably. Several candidate supermassive black holes have been identified at redshifts above 10, in galaxies existing when the universe was less than 500 million years old. Some of these objects appear to have black hole masses that represent a surprisingly large fraction of their host galaxy's total stellar mass, much larger fractions than are typical in the local universe, where the black hole mass is usually about 0.1 to 0.5% of the total stellar mass. This apparent overmass of early black holes relative to their host galaxies suggests that in the very early universe, black holes may have grown faster than their host galaxies, the reverse of what happens later in cosmic history. Understanding the origin, growth, and coevolution of supermassive black holes and their host galaxies is one of the central unsolved problems in astrophysics, and Webb's observations are both constraining existing models and generating new theoretical puzzles. While Webb's deep universe observations have captured most public attention, the telescope has also been transforming our understanding of planets orbiting other stars, exoplanets. One of Webb's most significant near-term capabilities is the characterization of exoplanet atmospheres through transit spectroscopy, measuring how starlight filters through a planet's atmosphere as it passes in front of its host star. In September 2022, Webb made headlines with the detection of carbon dioxide in the atmosphere of the exoplanet WSP-39b, a gas giant orbiting very close to its host star about 700 light-years from Earth. While this was not the first detection of atmospheric molecules in an exoplanet, that distinction belongs to earlier space telescopes. The quality and detail of Webb's spectroscopic data were unprecedented. The detection of carbon dioxide was significant not just as a molecular detection but as a demonstration of Webb's capability. If it can detect CO2 in a Jupiter-like atmosphere, it will eventually be able to probe the atmospheres of smaller, potentially habitable rocky planets with far greater sensitivity. Webb has subsequently detected a rich chemistry in WSP-39b's atmosphere, including sulfur dioxide, a molecule whose presence suggests active photochemical reactions driven by stellar ultraviolet radiation. The observation of photochemistry in an exoplanet atmosphere was itself a first, and it demonstrated that the chemistry of exoplanet atmospheres is complex, dynamic, and potentially far richer than previous models had predicted. The longer-term implications for the search for life are profound. Webb is beginning to turn its instruments towards smaller, potentially habitable rocky planets, most notably the 7 Earth-sized worlds of the TRAPPIST-1 system, which orbits an ultra-cool red dwarf star about 39 light-years from Earth. 3 of these planets, TRAPPIST-1F and TRAPPIST-1G, orbit within the system's habitable zone, where liquid water could potentially exist on a planetary surface. Webb's observations of these worlds are seeking to determine whether they have atmospheres at all, and if so, what those atmospheres are made of. This is science at the frontier of the impossible. Detecting the atmosphere of a small rocky planet around a dim red dwarf star 39 light-years away using spectroscopy is one of the most technically demanding observations in all of astronomy. Whether Webb has sufficient sensitivity to detect biosignatures, chemical signs of life, such as oxygen and methane together, remains uncertain and is the subject of active research. But the observations being made now are providing crucial data about the prevalence and properties of rocky planet atmospheres, laying the groundwork for the next generation of instruments. To appreciate fully why Webb's observations are so significant, it is necessary to understand the framework they are challenging. The lambda CDM model, often called the Standard Model of Cosmology, is the theoretical framework that has dominated cosmological thinking for the past 2 to 3 decades. It is by any measure a triumph of 20th and early 21st century science. Lambda CDM stands for lambda, representing the cosmological constant or dark energy, and CDM representing cold dark matter. The model describes a universe that began in the Big Bang approximately 13.8 billion years ago, expanded rapidly in a period of inflation, cooled and evolved through various phase transitions, formed the cosmic microwave background, developed the large-scale structure of the cosmic web through gravitational instability of cold dark matter, formed the first stars and galaxies, and continues to expand at an accelerating rate driven by dark energy. The successes of this model are impressive. It correctly predicts the relative abundances of light elements, hydrogen, helium, deuterium, lithium, produced in Big Bang nucleosynthesis. It accurately describes the acoustic peaks in the cosmic microwave background, the tiny temperature fluctuations in the afterglow of the Big Bang that encode information about the early universe's physics. It correctly predicts the large-scale distribution of galaxies, the cosmic web of filaments and voids observed in galaxy surveys. It explains the accelerating expansion of the universe, confirmed through observations of Type E supernovae in the 1990s. For these reasons, lambda CDM has been the reigning cosmological paradigm, but it has always had 2 large, embarrassing unknowns baked into its name: dark matter and dark energy, entities that together constitute approximately 95% of the total energy content of the universe, but neither of which has ever been directly detected or identified. Dark matter, the CDM of the model, is the name given to an unknown form of matter that does not interact with light, hence dark, but does interact gravitationally. Its existence is inferred from a variety of observations: the rotation curves of galaxies, which spin faster at their outskirts than the visible matter alone can explain, the gravitational lensing of light by galaxy clusters, the structure of the cosmic web, and the pattern of CMB fluctuations. Without dark matter, none of these observations can be reconciled with general relativity. Yet despite decades of direct detection experiments in deep underground laboratories, particle colliders and space telescopes, dark matter particles have never been directly observed. Dark energy, the lambda of the model, is even more mysterious. It is the name given to whatever is causing the universe's expansion to accelerate. In 1998, 2 independent teams of astronomers studying Type Ia supernovae found that distant supernovae were dimmer than expected. implying that they were farther away than a decelerating universe would predict. The universe was not slowing down under gravity as expected. It was speeding up. Something was driving galaxies apart at an ever-increasing rate. That something, dark energy, appears to constitute about 68% of the total energy of the universe, but its physical nature is completely unknown. It might be the energy of the quantum vacuum, it might be a dynamical scalar field, or it might be a hint that general relativity needs modification on cosmic scales. Against this background of two fundamental unknowns, Webb is now delivering observations that strain the Standard Model's predictive power in specific quantitative ways. One of the most rigorous ways to test models of galaxy formation is to compare the predicted and observed galaxy stellar mass function, a statistical description of how many galaxies exist at each stellar mass at different epochs. The Standard Model, combined with detailed hydrodynamical simulations of galaxy formation, makes specific predictions about the number of very massive galaxies that should exist at high redshift. These simulations, projects like Illustris TNG, EAGLE, and FIRE, are extraordinary computational achievements. They follow the evolution of thousands of cubic megaparsecs of the universe from the Big Bang to the present day, tracking the behavior of dark matter, gas, stars, black holes, and various feedback processes, stellar winds, supernovae, AGN jets that regulate star formation. They reproduce many observed properties of the local galaxy population remarkably well, but they were not predicting the massive galaxies Webb is finding in the early universe in the numbers Webb is finding them. The discrepancy is not trivial. Some analyses suggest that the number of massive galaxy candidates observed by Webb at very high redshifts exceeds the predictions of the best simulations by factors of 10 to 100. A discrepancy of 1 to 2 orders of magnitude. This does not necessarily mean that the Standard Model is completely wrong. There are several possible explanations, each with different implications. First, the photometric redshift estimates for many of these galaxies could be systematically biased toward higher values. If some galaxies presumed to be at z greater than 10 are actually at z equals 4 or 5, they would not pose a challenge to the Standard Model. Spectroscopic confirmation of redshifts is essential, and this work is ongoing. Second, the stellar masses of these galaxies could be overestimated. Converting observed brightness into stellar mass requires assumptions about the star formation history, the initial mass function of stars, and dust extinction. If the early universe contained an unusual population of stars, for instance, a top-heavy initial mass function skewed toward very massive stars, the observed brightness could correspond to a lower total stellar mass than standard conversion factors suggest. Third, active galactic nuclei, supermassive black holes actively accreting matter, could be contributing to the observed brightness of some early galaxies, making them appear more luminous, and therefore more massive than they actually are. AGN contamination is a known source of systematic uncertainty in high redshift photometry. Fourth, and most intriguingly, the Standard Model itself may need revision. The efficiency of star formation in the early universe, the role of dark matter in seeding galaxy growth, the processes of feedback that regulate how quickly galaxies grow, any or all of these could be different in the early universe than our models assume. Webb's challenges to the Standard Model come in the context of another, pre-existing crisis in cosmology, the Hubble tension. The Hubble constant, denoted h0, describes the current rate of expansion of the universe. Different methods of measuring h0 give results that are inconsistent with each other at a statistically significant level. Measurements based on the cosmic microwave background, specifically from the Planck satellite, give a value of approximately 67.4 kilometers per second per megaparsec. Measurements based on local distance indicators, Cepheid variable stars and type supernovae in the nearby universe, consistently give higher values, around 73 kilometers per second per megaparsec. The discrepancy is about 8%, but the statistical significance of the disagreement has now reached beyond 5 sigma, the conventional threshold for claiming a genuine scientific discovery, or, in this case, a genuine scientific problem. Either one or both sets of measurements is systematically wrong, or the Standard Model is missing some ingredient that resolves the discrepancy. Candidates for the resolution include early dark energy, a hypothetical component of energy density that was significant in the early universe and subsequently diluted away, modifications to general relativity, additional neutrino species, and various other exotic additions to the Standard Model. Webb has made significant contributions to the Hubble tension debate. It has independently calibrated the Cepheid distance ladder by observing Cepheid variable stars in galaxies also containing type Ia supernovae, helping to check for systematic errors that could explain the tension. Its initial results have confirmed the high local value of h0, making it harder to attribute the tension to systematic errors in the Cepheid calibration. This is not yet a resolution, but it is an important piece of evidence. If the Hubble tension is real, if the Standard Model genuinely cannot account for the discrepancy between early universe and late universe measurements of the expansion rate, then cosmology faces a profound crisis. The resolution of that crisis will require new physics. One of the most physically fundamental questions raised by Webb's observations is, how were the early galaxies able to form stars so efficiently? In the standard picture of galaxy formation, star formation is a notoriously inefficient process tightly regulated by various feedback mechanisms. When gas collapses under gravity in a galaxy, it heats up. Hot gas does not collapse easily, it resists gravitational contraction. For star formation to occur, gas must be able to cool efficiently, shedding its thermal energy through radiation. The presence of heavy elements, carbon, oxygen, silicon, dramatically enhances the cooling efficiency of gas, because these elements have many more spectral lines through which they can radiate energy. In the very early universe, before stellar nucleosynthesis had produced heavy elements, gas cooling was much less efficient, dominated by molecular hydrogen. Moreover, once stars form, they pump energy back into their surrounding environment, through radiation, stellar winds, and eventually supernova explosions. This stellar feedback heats and disrupts the gas clouds that would otherwise form more stars, limiting the efficiency of star formation. In most galaxies we observe today, only a few % of the available gas is converted into stars over a Hubble time, the current age of the universe. But the massive galaxies Webb is finding in the early universe appear to have converted a much larger fraction of their gas into stars very quickly. Some analyses suggest star formation efficiencies in the very early universe that approach 20 to 50%, far higher than the Standard Model predicts. This means either that stellar feedback was less effective in the early universe, or that the gas cooling and accretion processes were faster and more efficient than our models assume, or that there was some other mechanism, perhaps related to the properties of dark matter or the intensity of the radiation field in the early universe, that facilitated rapid star formation. One intriguing possibility is that the first galaxies formed in a very different environment from later galaxies, an environment dominated by the cosmic microwave background radiation, which in the early universe was far more intense than it is today. This intense radiation field could have had complex effects on the thermodynamics of gas in early galaxies, potentially facilitating or hindering star formation in ways our models do not fully capture. Dark matter plays a central role in the Standard Model of galaxy formation. In the lambda CDM framework, dark matter collapses first under gravity, forming a cosmic scaffolding of dark matter halos, extended, roughly spherical distributions of dark matter, within which ordinary matter, gas, then falls, cools, forms stars and builds galaxies. The properties of dark matter, specifically, that it is cold, moving slowly relative to the speed of light at the time of structure formation, determine the characteristic scales at which structure forms and the hierarchical sequence in which small structures merge into larger ones. Cold dark matter predicts that structure formation proceeds bottom-up. Small structures form first, then merge hierarchically into larger and larger structures. This prediction is generally consistent with the large-scale structure of the universe we observe, but it has long faced challenges on small scales, the so-called small-scale crises of lambda CDM, including the missing satellites problem. The Standard Model predicts many more small satellite galaxies around the Milky Way than are observed, the too big to fail problem, and the Caucus problem. Webb's observations add a new dimension to this picture. If large, massive galaxies were forming earlier than cold dark matter predicts they should, this could be a sign that dark matter is not as cold as the Standard Model assumes. Alternative dark matter models, including warm dark matter, fuzzy dark matter, extremely lightweight bosons, and various self-interacting dark matter scenarios, predict different small-scale structure formation histories and could potentially allow large galaxies to form earlier by modifying the collapse and accretion history of dark matter halos. The challenge for these alternative dark matter models is to match all the observational constraints simultaneously, not just the early galaxy observations, but also the CMB power spectrum, the large-scale structure of the cosmic web, the Hubble tension, and the properties of the local galaxy population. Finding a dark matter model that satisfies all these constraints simultaneously is a significant theoretical challenge, and one that Webb's observations are helping to sharpen. Some theorists have gone further than simply modifying the properties of dark matter or the efficiency of baryonic processes within the standard framework. They have proposed more radical alternatives to lambda CDM itself. The most prominent alternative in the literature is MOND, modified Newtonian dynamics, proposed by Israeli physicist Mordechai Milgrom in 1983. MOND modifies the law of gravity at very low accelerations to reproduce the rotation curves of galaxies without invoking dark matter. While MOND is successful at explaining the internal dynamics of individual galaxies, it has serious difficulties explaining the large-scale structure of the universe, the acoustic peaks in the CMB, and the dynamics of galaxy clusters, areas where dark matter-based models excel. More sophisticated relativistic extensions of MOND, including tensor vector scalar gravity, TEVs, and MOND-like modified gravity frameworks, attempt to extend the idea to cosmological scales, but generally face serious challenges in reproducing the observed CMB spectrum and large-scale structure. Another class of alternative frameworks involves modifications to the Big Bang itself, including bouncing cosmologies, cyclic models, and modifications of inflation. In these frameworks, the early universe may have had different properties from those assumed in standard lambda CDM, potentially allowing for faster structure formation. It is important to note that none of these alternative frameworks has yet succeeded in providing a complete, internally consistent account of all cosmological observations. The standard lambda CDM model, despite its challenges, remains the best framework we have for explaining the totality of cosmological data, but the challenges posed by Webb's observations are motivating serious theoretical inquiry, and the history of science suggests that when observations persistently deviate from model predictions, the models eventually have to change. There is something deeply philosophical about the predicament that the James Webb Space Telescope has placed us in. We have built the most powerful astronomical instrument in history. We have pointed it at the earliest epochs of cosmic time, and what we have found is not confirmation of our models, but a universe that keeps surprising us, a cosmos that is consistently richer, stranger, and more complex than our theoretical frameworks predict. This situation is not unique to cosmology. It is the characteristic condition of science at its most vital. The moment when the best available theory encounters observations that it cannot fully explain, and a period of productive crisis begins. Thomas Kuhn, in his landmark 1962 work The Structure of Scientific Revolutions, described this as the beginning of a paradigm shift, a period when anomalous observations accumulate until they can no longer be absorbed by incremental adjustments to the existing paradigm, and a new framework emerges that recontextualizes all the prior evidence. We may be at such a moment in cosmology, or we may not. The anomalies may be resolved through careful measurement, improved simulations, and better understanding of systematic effects. Science does not always undergo revolution. Sometimes it undergoes refinement. But the philosophical point remains. Our best models of the universe are not the universe. They are maps, and the territory is always larger than the map. This epistemological humility is not a weakness. It is the source of science's power. Unlike systems of thought that claim infallibility, science builds in the possibility of its own revision. Every scientific theory carries within it the seeds of its own potential overthrow, the predictions that, if falsified, would demand a new theory. This is what makes science so extraordinarily successful at generating knowledge about the physical world. The James Webb Space Telescope is a machine for testing predictions against reality, and when reality does not match the predictions, science does not defend the predictions, it revises the models. This is happening right now in real time as astronomers analyze Webb's data and theorists scramble to understand what they mean. One of the most philosophically vertiginous aspects of Webb's observations is the encounter with deep time, with the reality that the universe has been evolving for 13.8 billion years, that the light Webb captures has been traveling for longer than the Earth has existed, and that the galaxies it reveals are not objects in the present universe but ghosts of the past, images of what was transmitted to us across an almost incomprehensible span of time. Deep time has always been a challenge to human intuition. Our evolutionary heritage equipped us to navigate a world on timescales of seconds, days, seasons, and human lifespans, not billions of years. When we try to grasp a span of time like 13.8 billion years, our intuition simply fails. We can manipulate the numbers mathematically, but we cannot feel them. And yet, somehow, looking at a Webb image forces a kind of felt encounter with deep time that mathematics alone cannot produce. When you look at the galaxies in Webb's first deep field and realize that each of those points of light is an island universe of hundreds of billions of stars, and that the light from the most distant of them left before the Earth existed, before the Sun ignited, before the Milky Way took its present form, something shifts in the mind. Not an intellectual recognition, but something more like a physical sensation of the depth and age of the cosmos. Philosophers have long grappled with the concept of deep time and what it implies for human meaning and significance. Some have found in it a source of existential vertigo, If the universe is 13.8 billion years old and humanity has existed for perhaps 300,000 years, we are cosmically negligible, a fleeting wrinkle in a tapestry of almost incomprehensible duration. On this view, the discoveries of cosmology are a kind of philosophical acid, dissolving the human-centered assumptions that have sustained cultures and civilizations throughout history. But there is another philosophical response, equally defensible and arguably more generative. It is the response of wonder, the recognition that whatever else we may be, we are the part of the universe that can look back at itself across 13.8 billion years of history and understand what it sees. We are the cosmos become self-aware. The hydrogen atoms that make up our bodies were forged in the Big Bang. The carbon in our cells was created in the cores of dying stars. The iron in our blood was scattered across space by supernova explosions billions of years before the Earth existed. We are, as Carl Sagan famously said, made of star stuff. And the James Webb Space Telescope is the instrument through which that star stuff contemplates its own origins. Webb's observations of the early universe also touch on one of the deepest philosophical and scientific puzzles in contemporary cosmology, the fine-tuning problem. The laws of physics as we understand them contain various fundamental constants: the strength of gravity, the strength of the electromagnetic force, the mass of the electron, the cosmological constant, that must be extremely precisely calibrated for a universe like ours containing stars, planets, and complex chemistry to exist. If the cosmological constant, the term in Einstein's equations associated with dark energy, were even slightly larger than it is, the universe would have expanded so rapidly that matter could never have clumped together to form galaxies, stars, or planets. Life would be impossible. If it was slightly smaller or negative, the universe would have rapidly recapitulated. The fact that the cosmological constant has the extremely small but non-zero value it appears to have, what physicists call the coincidence problem, is one of the deepest unsolved problems in theoretical physics. Similarly, if the ratio of the electromagnetic force to gravity were slightly different, stars could not burn stably for billions of years. If the masses of quarks were slightly different, protons would not be stable. If the Big Bang had produced matter and antimatter in exactly equal proportions, rather than the very slight excess of matter over antimatter that exists, they would have annihilated each other completely, leaving a universe containing nothing but radiation. The existence of a universe complex enough to contain observers seems to depend on a very precise tuning of these fundamental parameters. The philosophical responses to this fine-tuning are several. The anthropic principle, in its various forms, points out that we can only observe a universe in which the conditions for our existence are met. This is logically tautological, but it has explanatory content when combined with a multiverse hypothesis. If there are a vast number of universes with different physical laws and constants, most of them will be lifeless, and observers will only ever find themselves in the relatively rare universes hospitable to their existence. The multiverse is a deeply controversial concept, not just philosophically but scientifically. Its proponents argue that it is a logical consequence of well-established theoretical frameworks like eternal inflation and string theory. Its critics argue that it is untestable and therefore scientifically sterile, a hypothesis that can never be confirmed or refuted. The debate continues, and Webb's observations cannot directly resolve it, since the multiverse by definition comprises causally disconnected regions of spacetime that we can never observe. But Webb's observations of a universe that appears to be even more finely structured in its early history than previously thought add a new dimension to the fine-tuning discussion. If the early universe was producing massive, chemically enriched galaxies hundreds of millions of years earlier than our models predicted, this suggests that the conditions for complex chemistry, and potentially for life, were present in the universe much earlier than we thought. The time for life to emerge in the cosmos may be longer, and the cosmic stage for it may be larger than we imagined. The James Webb Space Telescope operates in a realm that many religions and philosophies have traditionally reserved for the sacred, the question of origins. Where did the universe come from? How did it develop? Where is it going? These are not merely scientific questions. They are the deepest questions of human existence, questions that have animated religion, philosophy, mythology, and art throughout recorded history. Modern cosmology provides answers to these questions that are empirically grounded, mathematically precise, and philosophically challenging. The universe began in an extraordinarily hot, dense state about 13.8 billion years ago. It expanded and cooled. Quantum fluctuations in the inflationary epoch seeded the density perturbations that gravity subsequently amplified into the cosmic web, and from that web arose galaxies, stars, planets, and eventually life. The universe has no center, no edge, no fixed moment of ending. though it will eventually end in some sense in the far future as stars burn out and black holes evaporate. And it did all of this, apparently, without purpose, without intention, without a plan, through the blind operation of physical laws on the primordial quantum foam. This picture is deeply challenging for any philosophy of cosmic meaning. If the universe is simply the product of physical laws operating on initial conditions, where does purpose come from? Where does meaning come from? These questions do not have scientific answers. They are philosophical and existential questions, questions about the human relationship to the physical world that cosmology reveals. Some philosophers and scientists have argued that meaning must be created rather than discovered, that the universe is not inherently meaningful, and that human beings generate meaning through their projects, relationships, and commitments. This existentialist response to the meaninglessness of the cosmos is coherent and dignified, but it leaves open the question of whether human-generated meaning can be sufficient in the face of the true scale of cosmic history. Others have argued that meaning and purpose emerge naturally from the structure of the universe itself, not as external impositions but as genuine features of complex, self-organized systems. On this view, consciousness, meaning, and purpose are not anomalies in a meaningless physical universe, but natural consequences of the universe's self-organizing complexity. The universe does not have a purpose imposed upon it from outside, but it generates purpose from within, through the emergence of minds capable of caring, reflecting, and choosing. Webb's observations of a universe that appears to be more complex, more organized, and more rapidly self-organizing in its earliest moments than we thought gives indirect support to this second view. A universe that was cooking up complex, chemically enriched galaxies within the first 300 million years of its existence is a universe that was, from very early on, in the business of creating the conditions for complexity. Whether that complexity culminated, in our particular corner of this particular galaxy, in beings capable of wondering about it, remains one of the most astonishing and unanswered questions in all of philosophy. There is a deeper philosophical challenge lurking behind Webb's observations, one that goes beyond the specifics of cosmology to the question of the limits of human knowledge itself. We are biological creatures, evolved to survive on the surface of a small rocky planet in a temperate solar system, in a quiet corner of a spiral galaxy. Our brains evolved to process the sensory information relevant to our survival, the shapes of predators, the faces of other humans, the patterns of seasons and weather. They did not evolve to intuitively grasp quantum mechanics, general relativity, or cosmology. Yet here we are, using the extraordinary products of our collective intelligence, telescopes, particle accelerators, mathematical frameworks, computers, to probe the structure of the cosmos at scales ranging from the subquantum to the cosmic web. This is one of the most remarkable facts about the human species, that brains evolved for survival on the African savanna can, through science, comprehend the geometry of space-time, the nuclear physics of stellar interiors, and the thermal history of the early universe. But comprehend is perhaps too strong a word. We can model these things. We can write equations that accurately predict observations over an extraordinary range of scales and conditions. But do we truly understand a universe in which 95% of the energy matter content, dark matter and dark energy, has never been directly detected? Do we understand a universe that appears to be fine-tuned for complexity to a degree that demands explanation? Do we understand a universe whose earliest moments are revealing a pattern of rapid, efficient galaxy formation that our best models cannot fully account for? Perhaps the most honest answer is that we partially understand, that our models capture genuine features of reality but are inevitably incomplete, inevitably limited by the fact that we are embedded observers within the system we are trying to understand. There may be aspects of the cosmos that are, in principle, beyond human comprehension, not because we are not intelligent enough, but because the universe contains dimensions of reality that our biological and cognitive constitutions simply cannot access. The philosopher Immanuel Kant argued that the human mind does not passively receive information from reality. It actively structures experience through innate categories of understanding, space, time, causality. On this view, we can only ever know phenomena, the world as it appears to minds like ours, not the thing in itself, the noumenon, the world as it actually is independent of any observer. The discoveries of 20th and 21st century physics have given this Kantian intuition unexpected resonance. Quantum mechanics tells us that the act of observation influences the state of the observed system. Relativity tells us that space and time are not fixed backdrops but dynamical entities whose properties depend on the observer's reference frame. These are not just technical results. They are invitations to think deeply about the relationship between observer and observed. between the mind and the cosmos, there is one philosophical response to the discoveries of the James Webb Space Telescope that transcends all the debates about fine-tuning, meaning, and the limits of knowledge: wonder. Raw, untheorized, visceral wonder at the strangeness and richness of the universe we inhabit. Wonder is not a scientific concept. It is not a variable that appears in cosmological equations, but it is arguably the engine that drives science forward. The capacity to be surprised, to find one's expectations violated by reality, to stand before the unknown not with fear but with excitement. This is the psychological substrate from which scientific inquiry grows. The greatest scientists in history have always been people who never lost the ability to be astonished, who maintained, even in the midst of technical mastery, the sense that reality is inexhaustibly stranger and richer than any theory. The James Webb Space Telescope, in this sense, is not just a scientific instrument, it is a wonder-generating machine. Its images of galaxies billions of years old, of stellar nurseries where new suns are being born, of the ancient architecture of the cosmic web, are not merely data. They are encounters with the sublime. They place the human mind in direct contact with scales of space, time, and complexity that exceed its ordinary grasp, and in doing so they produce a specific kind of experience, one that has been central to human culture, philosophy, and religion throughout history: the encounter with the vast. The Romantics had a concept for this experience: the sublime. For Edmund Burke and Immanuel Kant, the sublime was the experience of encountering something so vast, so powerful, or so complex that it exceeded the capacity of ordinary aesthetic experience and produced a mixture of awe, terror, and exhilaration. The night sky has always been one of the primary sources of the sublime for human beings. What the James Webb Space Telescope does is extend the sublime beyond the boundaries of the visible sky, into regions of space and time that no human eye had ever before accessed, and make those regions perceptible. This is not a trivial achievement. In an age of deep cynicism, fragmented attention, and existential anxiety, the images from Webb have provoked something remarkable: genuine, widespread awe. People who know nothing about cosmology have looked at Webb's first deep field and felt something profound. Scientists who have spent decades studying galaxy formation have looked at Webb's earliest galaxy observations and felt not triumph but humility. The humility of the researcher who realizes that nature is always more creative than their models. Wonder, in this sense, is not the enemy of knowledge. It is its precondition. The scientific response to Webb's challenging observations is already well underway. Theoretical astrophysicists and cosmologists around the world are working to understand whether Webb's findings can be accommodated within a modified version of the standard Lambda CDM framework, or whether more fundamental revisions are required. Several specific directions of theoretical inquiry are particularly active. One is the refinement of galaxy formation simulations. Existing simulations like Illustris-DNG were calibrated primarily to reproduce the properties of the local universe. Running new simulations specifically designed to probe the high redshift regime with higher resolution and more sophisticated physical prescriptions for feedback processes is a priority. Early results from some of these new simulation efforts suggest that modifications to the treatment of stellar feedback, specifically allowing for more rapid, bursty star formation in the early universe, can produce more massive early galaxies without violating other observational constraints. Another active area is the population of stars in early galaxies. If the first galaxies were dominated by very massive stars, population 3 stars, these stars would be far more luminous per unit of stellar mass than the stars typical in the local universe, potentially explaining why early galaxies appear more massive than they actually are when standard mass-to-light ratios are applied. Models with top-heavy initial mass functions in early galaxies are being tested against Webb's photometric and spectroscopic data. The role of active galactic nuclei in early galaxy evolution is also receiving intense theoretical attention. If AGN activity was more common and more influential in the very early universe than assumed in standard models, both in driving star formation through positive feedback and in quenching it through negative feedback, this could significantly alter the predicted properties of early galaxies and potentially bring simulations into better agreement with observations. The process of model revision in response to observations is not a sign of failure. It is how science works. Every time observations exceed the predictions of a theory, the theory gets better. The discrepancies Webb is revealing are not embarrassments for cosmology. They are opportunities, data points that, when understood, will constrain the next generation of more accurate, more comprehensive models of the universe's history and structure. Webb is not operating in isolation. It is part of a larger ecosystem of current and planned astronomical instruments that together are transforming our observational grasp of the cosmos. The Atacama Large Millimeter Array, AMI in Chile, an interferometer of 66 radio antennas operating at millimeter and sub-millimeter wavelengths, is a powerful complement to Webb. While Webb observes the rest frame ultraviolet and optical light from early galaxies, redshifted into the near-infrared, ALMA observes the cold gas and dust in those same galaxies, providing information about the raw material available for star formation. The combination of Webb and ALMA observations provides an extraordinarily complete picture of the physical state of early galaxies. The Euclid Space Telescope, launched by the European Space Agency in 2023, is conducting a wide-field survey of the sky, designed to map the large-scale structure of the universe with unprecedented precision. Its primary goals are to constrain the nature of dark energy and dark matter through measurements of galaxy clustering and weak gravitational lensing. Euclid's survey data will provide a large-scale context for Webb's deep-field observations, connecting the small-scale detailed studies of individual galaxies and galaxy clusters to the statistical properties of the cosmic web. The Nancy Grace Roman Space Telescope, previously known as FIRST, is planned for launch in the late 2020s. With a mirror the same size as Hubble but a field of view 100 times larger, Roman will conduct deep sky surveys that combine the depth of Hubble's deep fields with the wide coverage of ground-based surveys. It will observe millions of galaxies at high redshift, providing the statistical sample needed to test models of galaxy formation and evolution at a level of precision currently impossible. Looking further ahead, the extremely large telescope, ELT, currently under construction on Cerro Armazones in Chile by the European Southern Observatory, will be the world's largest optical telescope when it opens in the late 2020s. With its 39-meter primary mirror, it will be able to obtain spectroscopic observations of faint high redshift galaxies that are currently too faint for detailed spectroscopic analysis. The combination of ELT spectroscopy with Webb imaging will enable a new level of physical understanding of early galaxy populations. These instruments, working together, represent a new era of multi-wavelength, multi-messenger astronomy, one in which the cosmos is probed simultaneously at many wavelengths, from radio to gamma rays, and in which gravitational wave observatories like LIGO Virgo and the planned space-based LISA add an entirely new channel of cosmic information. We are moving from an era of telescopes to an era of observatories in the fullest sense. Coordinated networks of instruments probing reality at every accessible scale and wavelength. Among the most exciting long-term implications of Webb's observational program is its contribution to the search for extraterrestrial life. This contribution is primarily indirect. Webb is not searching for alien civilizations, and it is not yet capable of detecting biosignatures in the atmospheres of Earth-like planets. But its observations are transforming our understanding of the cosmic context of life in several important ways. First, Webb's observations of the early universe are extending the timeline of potentially habitable environments. If the universe was producing chemically enriched galaxies, galaxies containing carbon, oxygen, silicon, and other biologically important heavy elements, within the first few 100 million years of cosmic history, then the cosmic prerequisite for life, the existence of heavy elements, was satisfied much earlier than previously thought. Life potentially could have emerged in the universe billions of years earlier than we might have expected. Second, Webb's observations of star-forming regions within the Milky Way are providing new information about the process by which planetary systems form and about the chemical complexity of the protoplanetary environment. Webb has detected complex organic molecules in the gas and ice of protostellar clouds, molecules like dimethyl ether and methyl formate that are precursors to amino acids and other biologically important compounds. These detections suggest that the chemical building blocks of life are assembled before planets even form, in the cold, dense molecular clouds from which stars and planetary systems emerge. Third, Webb's atmospheric characterization of exoplanets, while currently focused on large, hot gas giants, is laying the technical groundwork for the characterization of smaller, potentially habitable worlds. The experience gained from analyzing the spectra of hot Jupiter atmospheres, understanding systematic effects, instrumental artifacts, data reduction techniques, will be directly applicable when Webb turns its instruments toward more challenging targets, and Webb's eventual observations of the TRAPPIST-1 planets will represent the first serious attempt to characterize the atmospheres of potentially habitable rocky worlds. The question of whether life exists elsewhere in the universe is one of the most profound questions in science, perhaps in all of human thought. The James Webb Space Telescope will not answer that question, but it is contributing, piece by piece, to the scientific foundation from which the eventual answer will emerge. Science does not exist in isolation from culture. Major scientific discoveries have profound social and cultural effects, shaping how societies understand themselves and their place in the cosmos. The discoveries of the Copernican revolution, of evolution by natural selection, of the Big Bang, each of these fundamentally altered the human self-image and prompted new philosophical, religious, and cultural responses. Webb's discoveries are already having cultural effects. The telescope's first images went viral the moment they were released, reaching billions of people around the world in hours. Social media platforms were flooded with reactions ranging from awe and wonder to philosophical reflection to existential anxiety. For a brief moment, the ancient human practice of looking at the stars became a global, shared experience mediated by digital technology but rooted in the oldest of human impulses. The cultural impact of Webb is likely to deepen as more discoveries are made and their significance becomes more widely understood. The challenge of communicating the implications of Webb's science to a general audience is considerable. It requires translating highly technical results into language accessible to non-specialists without oversimplifying to the point of distortion. Science communicators, journalists, educators, and artists all have a role to play in this translation. There is also a political and economic dimension to Webb's cultural impact. The telescope is a product of international scientific cooperation involving NASA, the European Space Agency, and the Canadian Space Agency, and drawing on scientific talent and technical capability from across the world. At a time of increasing nationalism and geopolitical tension, Webb represents an alternative model, the possibility of international collaboration on projects of genuine civilizational significance, producing knowledge that belongs to all of humanity. The economic implications of Webb's technological innovations should also not be overlooked. The development of Webb required advances in mirror fabrication, cryogenic engineering, infrared detector technology, spacecraft systems, and computational methods that have applications far beyond astronomy. The history of investment in fundamental science is replete with examples of technological developments motivated by pure research that subsequently found applications in medicine, communications, computing, and industry. Webb's discoveries are also driving transformation in scientific education and research institutions. The telescope's data is publicly available. Anyone in the world with the skills to analyze it can download Webb observations and potentially make new discoveries. This democratization of scientific data is one of the most significant changes in the practice of astronomy in the modern era. The community of Webb users extends far beyond the traditional astronomical research community. Citizen scientists, amateur astronomers, and members of the public are contributing to data analysis through projects like Galaxy Zoo, which has enlisted hundreds of thousands of volunteers to classify galaxies in sky surveys. Machine learning and artificial intelligence are being applied to Webb's data at scale, identifying patterns, sources, and anomalies that would be impractical to find through manual inspection. The combination of expert scientific analysis, citizen science, and AI-assisted discovery is transforming the sociology of astronomical research. Educational institutions are also responding to Webb's discoveries. Curricula from secondary school through university are incorporating Webb's findings, using its images and data to engage students with fundamental questions in physics, astronomy, and the philosophy of science. The telescope's combination of visual beauty, scientific depth, and philosophical richness makes it an extraordinary educational resource, one that can engage students who might otherwise find science abstract or inaccessible. Research institutions are shifting their priorities and resources in response to Webb's findings. Theoretical astrophysics groups are redirecting their efforts toward the high redshift galaxy formation problem. Observational programs are being restructured to capitalize on Webb's capabilities. Funding agencies are responding to the demonstrated scientific productivity of Webb by prioritizing next-generation instruments and missions that can follow up on its discoveries. The long-term trajectory of cosmology, shaped in part by Webb's discoveries, points toward a period of significant theoretical innovation. The challenges that Webb's observations are posing to the standard lambda-CDM model, the two early massive galaxies, the surprisingly efficient early star formation, the rapidly evolving supermassive black holes, the unexpectedly chemically enriched early universe, are not going to be resolved by minor parameter adjustments. They may require genuinely new physics. What form might that new physics take? The possibilities are numerous and fascinating. One direction is a better understanding of dark matter, moving beyond the simple cold dark matter paradigm to models that better predict the observed distribution and properties of small-scale structure. Another direction is a better understanding of dark energy, moving beyond the simple cosmological constant to models of dynamical dark energy that could help resolve the Hubble tension and potentially explain aspects of early universe structure formation. A third direction involves the physics of the inflationary epoch, the extremely brief period of exponential expansion that is thought to have occurred in the first tiny fractions of a second after the Big Bang. Inflation is invoked in the Standard Model to explain the large-scale homogeneity and isotropy of the universe, the near-flatness of spatial geometry, and the origin of the density perturbations that seeded structure formation. But the detailed physics of inflation, what caused it, what field drove it, and exactly how it ended, remain poorly understood. Modifications to inflationary models could significantly affect the predictions for the early universe and potentially reconcile the observed early galaxy population with theoretical expectations. Perhaps most exciting is the possibility that Webb's discoveries point toward entirely new fundamental physics, new particles, new forces, new symmetries that have not yet been theorized. The history of physics is full of cases where observational anomalies led to discoveries that were not just quantitative refinements, but qualitative transformations of understanding. The perihelion precession of Mercury that pointed toward general relativity, the ultraviolet catastrophe that pointed toward quantum mechanics, the anomalous magnetic moment of the electron that pointed toward quantum electrodynamics. Webb's anomalies could be the equivalent harbingers of a new era. The James Webb Space Telescope has now been operating for several years, delivering observation after observation that simultaneously confirms the extraordinary power of human science and reveals the humbling incompleteness of our current understanding. It is a fitting symbol of where humanity stands in the 21st century, possessed of extraordinary technological capability, generating knowledge at an unprecedented rate, and simultaneously confronting the depth of our remaining ignorance. What are the lessons of Webb? Let us count them. The first lesson is that reality is always more complex than our models. Every great advance in astronomy has revealed a universe larger, older, stranger, and more detailed than previously known. Webb is no exception. Its images of the early universe show a cosmos that was already, in its first few 100 million years, busily creating the structures and processes that would eventually, billions of years later, produce the conditions for life. The early universe is not the simple, smooth, undifferentiated place our models implied. It is already organized, already complex, already producing the hierarchies of structure that characterize the cosmos we inhabit. The second lesson is that observation drives theory. For all the power of mathematical physics and theoretical cosmology, it is ultimately the confrontation with the observed universe that determines which theories survive and which do not. Webb's observations are forcing theorists to revisit assumptions they had previously taken for granted about star formation efficiency, about the growth of supermassive black holes, about the role of feedback in regulating galaxy growth. This is how science progresses. Theory proposes, observation disposes. The third lesson is that the universe is not only larger than we imagined, it is older, not in the sense of having a greater total age, but in the sense that complexity arrived earlier than we thought. The seeds of the cosmic web, the first massive galaxies, the first chemically enriched stellar populations, all of these appear to have emerged significantly earlier in cosmic history than our models predicted. The universe, it seems, did not waste its early years. The fourth lesson, perhaps the deepest, is about the nature of human knowledge and the relationship between knowing and being. We are creatures of the cosmos who have developed the capacity to turn our instruments and our minds toward the cosmos and read its history. This is an extraordinary fact about our existence, a fact that neither science nor philosophy has fully assimilated. The capacity for cosmological knowledge is itself part of the universe's self-expression. Webb is not an alien instrument imposed on the cosmos from outside. It is a product of the cosmos, built by creatures who are part of the cosmos, observing a cosmos that contains them. Webb's observations have not closed questions, they have opened them. And the questions now standing before cosmology and philosophy are more interesting, more challenging, and more significant than the ones that preceded them. How did the early universe produce such massive, chemically enriched galaxies so quickly? What physical processes, known or as yet unknown, drove such rapid and efficient star formation in the first few 100 million years of cosmic history? What is the nature of dark matter, and how did it shape the earliest structures? What is dark energy, and does its behavior change over cosmic time? How did supermassive black holes grow to such enormous masses so early? What drove the reionization of the universe, and how did that process shape the subsequent evolution of galaxies? And below all of these scientific questions, are we alone? Did the conditions that produced complex chemistry and eventually life in our corner of the cosmos produce similar outcomes elsewhere? How common is life in a universe that appears to have been making complex structures since very early in its history? These are not merely scientific questions, they are existential questions. They are questions about the nature of reality, the place of life in the cosmos, and the relationship between conscious minds and the physical universe they inhabit. The James Webb Space Telescope is, in this sense, not just an instrument for studying galaxies and stars. It is a philosophical provocation of the highest order, a machine that forces us to confront the limits of our knowledge, the depth of our ignorance, and the inexhaustible strangeness of the reality in which we find ourselves. In the final analysis, the most profound thing about the James Webb Space Telescope may not be what it finds, but what the act of looking means. Human beings have always looked at the sky. Before telescopes, before science, before writing, our ancestors looked up at the stars and felt something: wonder, awe, curiosity, perhaps a sense of connection to something larger than themselves. They wove the stars into stories, into calendars, into navigation systems, into myths of origin and destiny. The sky was not just backdrop, it was meaning. Modern science has not eliminated that meaning, it has deepened it. When we now look at the stars, we look with knowledge. Knowledge of their physical nature, their distances, their temperatures, their life cycles. We look at the Milky Way and know we are seeing the combined light of hundreds of billions of suns. We look at a distant smudge and know it is a galaxy, a universe unto itself, billions of light years away. And now, with Webb, we look at the faintest, most distant points of light in the deepest sky images ever made, and we know we are seeing the universe in its infancy, seeing light that has been travelling toward us for longer than the Earth has existed. This knowledge does not diminish the wonder, it transforms it. The wonder of ignorance, the wonder of looking at the unknown, is real and beautiful. But the wonder of knowledge, the wonder of looking at the known and realizing how much more there is to understand, is greater. It is the wonder of the explorer who reaches a hilltop and sees, spread out before them, a landscape of astonishing complexity and beauty that extends far beyond what any map has shown. The James Webb Space Telescope looked too deep into space, and what it found was not the answer to our cosmological questions, but the beginning of a new chapter of questions, stranger, richer, and more beautiful than the chapter that preceded it. It found a universe that refuses to be fully known, that always holds something in reserve, that always has one more surprise waiting in the ancient light. And in finding that, it found exactly what science, at its best, at its most honest, at its most alive, always finds: not the end of the road, but the beginning of a longer, more winding, more wonderful journey into the dark. There is something that looks very much like love in the act of building the James Webb Space Telescope. Not romantic love, but something deeper and less sentimental. The love of a craftsperson for their work, the love of a parent for a child they have made, the love of an explorer for the unknown territory they are entering. Think of what Webb required: decades of painstaking design and engineering, contributions from thousands of people across dozens of countries, billions of dollars, and the willingness to take extraordinary risks. The risk that the sunshield would not deploy, that the mirror would not unfold, that one of the 344 single point of failure mechanisms would fail. The people who built Webb knew this. They built it anyway. They built it because they wanted to see, because the drive to know, to understand, to push the boundaries of the observable universe is one of the deepest and most characteristically human impulses. The images that Webb has returned are beautiful, not just because they are aesthetically striking, but because they are true. They are accurate representations of the actual structure of the cosmos, of galaxies, nebulae, and star clusters that actually exist, that are actually as magnificent as they appear. There is a kind of truth beauty in scientific imagery that is different from artistic beauty, but no less powerful. The beauty of seeing reality clearly, without illusion, without sentimentality. When a child looks at a Webb image of a stellar nursery, the pillars of creation, the Carina Nebula, the birth of stars in columns of gas and dust, and feels wonder, that wonder is not naive, it is appropriate. It is proportionate to the reality it is responding to. The cosmos is genuinely, objectively, measurably extraordinary. Science does not destroy that wonder. It confirms it, grounds it, and deepens it. The James Webb Space Telescope looked too deep into space. What it found was a universe more ancient, more complex, more self-organizing, and more surprising than we had imagined. What it found was a universe that has been building toward complexity since its earliest moments. What it found was the light of ancient galaxies bearing witness to 13.8 billion years of cosmic history. And what it found, ultimately, was a mirror, a vast ancient mirror in which we can see, if we look carefully enough, the long road that led from the quantum fluctuations of the inflationary epoch to the moment when beings made of star stuff looked up at the sky and asked, "Where did we come from? Where are we going? And are we alone?" These questions do not have final answers. They may never have final answers, but the asking of them, the persistent, passionate, rigorous asking of them, generation after generation, instrument after instrument, is itself one of the greatest expressions of what it means to be human. And the James Webb Space Telescope, peering through time and space at the oldest light in the cosmos, is the finest instrument that expression has yet produced. We are standing at the edge of everything, and we are just beginning to see. Consider what it means that the universe permits this kind of inquiry. That the same physical laws that govern the burning of stars, the formation of galaxies, and the expansion of space-time also permit the emergence of beings who can sit in front of a computer screen, analyze data from a telescope floating 1.5 million kilometers from Earth, and ask, what does this mean? There is a phrase that the physicist Freeman Dyson used, in a different context. The universe is an unexpectedly hospitable place for living beings to make their home in. Webb's observations have, in a paradoxical way, deepened this sense of hospitality, not because they have made the universe less frightening or more comprehensible, but because they have revealed that complexity, the kind of complexity from which life emerges, is not a rare, late, barely possible accident. It is something the universe began producing very early, with great efficiency across vast scales. The galaxies Webb observes at redshift 14, those specks of ancient light from 290 million years after the Big Bang, are not alien to us. They are our deep ancestors. The heavy elements those galaxies synthesized in their first generation of massive stars, the carbon, oxygen, nitrogen, iron, were scattered into the cosmos when those stars exploded as supernovae. Over the next 13 billion years, those elements were incorporated into subsequent generations of stars, into planetary systems, into the chemistry of life on at least one small rocky world. The carbon in your body may have been forged in a stellar nursery visible in the light of a galaxy that Webb is now photographing. We are not separate from the universe we are studying. We are its continuation, its elaboration, its most recent expression of self-organized complexity. The James Webb Space Telescope did not look into the past of some other universe. It looked into our past, into the history of the matter and energy that constitutes every one of us. Every great scientific instrument tells a chapter of the universe's story. Galileo's telescope told the chapter of the solar system. Hubble's telescope told the chapter of the expanding universe. Now the James Webb Space Telescope is telling the chapter of the first light, the epoch when the universe went from dark to bright, from simple to complex, from formless to structured. But this chapter is not finished. Webb will continue operating for at least 2 decades. In that time, it will observe hundreds of galaxies at redshifts above 10, providing a statistical characterization of the early galaxy population that will either confirm or refute the emerging picture of early efficient structure formation. It will characterize the atmospheres of dozens of exoplanets, building a library of comparative planetary atmospheres that will be the foundation for future life detection missions. It will map the distribution of heavy elements in early galaxies, tracing the chemical history of the cosmos. It will observe the formation of planetary systems in the making, watching the process by which disks of gas and dust around young stars coalesce into planets. And as it does all of this, it will, with near certainty, reveal things we did not predict, observations that will require new theories, new models, new frameworks. That is the nature of science at the frontier. The map never catches up with the territory. Reality is always ahead. One of the intellectual virtues that Webb's discoveries invite us to cultivate is the courage to not know, the willingness to say, our models do not fully account for this, without immediately rushing to fill the gap with speculation, or to dismiss the anomaly as measurement error. Science advances not by avoiding uncertainty, but by sitting with it long enough to understand it clearly, and then bringing the full force of disciplined inquiry to bear on its resolution. The cosmologists and astrophysicists now grappling with Webb's challenging data are demonstrating this courage. They are neither dismissing the anomalies nor overinterpreting them. They are doing the painstaking, unglamorous work of spectroscopic follow-up, of improved simulations, of error analysis, of theoretical exploration, work that will eventually determine whether we are witnessing minor discrepancies requiring modest model adjustments, or major anomalies pointing toward new fundamental physics. The outcome of that work is not yet determined, but the work is underway, and it is among the most important scientific work being done on Earth right now. In laboratories and observatories and university offices around the world, human minds are wrestling with the data from a telescope that looked too deep into space, and finding that the universe it revealed is stranger, richer, and more inviting of wonder than they had previously known. In 1995, the Hubble Space Telescope pointed at a tiny, seemingly empty patch of sky in the constellation Ursa Major and stared at it for 10 days. The resulting image, the Hubble Deep Field, revealed nearly 3,000 galaxies in that single patch of sky, most of them never previously seen. It was a revelation. The universe was not sparse and empty. It was overwhelmingly, almost incalculably full. The James Webb Space Telescope's deep fields are in one sense a continuation of this tradition. But they go further, deeper in time, richer in detail, more revealing in their science. Where Hubble showed us that the universe is full, Webb is showing us that it has always been full. That structure, complexity and organization were present from the very earliest epochs of cosmic history. This is a gift, not in a sentimental sense but in a genuine epistemological sense. It is a gift of knowledge, of true information about the nature of the reality we inhabit. It is the kind of gift that only the universe itself can give, and only through the combined intelligence, creativity and labour of a scientific civilization that has spent centuries learning how to receive it. We are such a civilization. We are, despite our manifold failures and contradictions, a species that builds telescopes, peers into the ancient darkness and tries to understand what it sees. The James Webb Space Telescope is the current summit of that aspiration, the most powerful eye we have ever turned toward the cosmos. What it has seen has humbled us. What it has seen has astonished us. What it has seen has forced us to revise our best theories and confront the depth of our remaining ignorance. And what it will continue to see, in the months and years and decades ahead, will, with the certainty that science's history promises, surprise us again. The universe is not finished telling its story, and we are not finished listening. The cosmos is all that is, or ever was, or ever will be. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbour life. There is nowhere else, at least in the near future, to which our species could migrate. Visit? Yes. Settle? Not yet. Like it or not, for the moment the Earth is where we make our stand. Carl Sagan, Pale Blue Dot, 1994, and yet the James Webb Telescope has shown us that the stage is far larger and the story far older than even Sagan knew. We are not just inhabitants of a pale blue dot, we are expressions of a 13.8 billion-year experiment in complexity, an experiment that began in earnest, it seems, within the first few 100 million years of cosmic history, and that is still gloriously underway.